Okay, in this video we're going to look at how to interpret a photoelectron spectrum that it hasn't been printed out to scale. Now this can happen sometimes when the intensity on the spectrophotometer is turned up too high. We can end up with peaks that don't make sense to an electron configuration, or they're not exactly to scale to a perfect electron configuration. What that means exactly is, if we look at the previous example, each one of these peaks landed on the exact number of electrons that the orbital has. For instance, right here in the s orbital, the 1s, the peak stopped at 2, because that is the maximum amount of electrons any s orbital can hold. Same thing with the 2s orbital. Again, the 2 electrons is the max that any s orbital can hold. For the 2p orbital, it maxed out at 6, because that's the maximum amount of electrons the 6 or the 2p orbital can hold, so forth and so on. In this case over here, these peaks are not to scale because maybe the intensity on the spectrophotometer was turned up a little too high. And this can happen and result in what I like to call a spectrophotometer, or a spectrum that's been overread, if you will. So let's try to interpret this. There still is a way we can figure out what this mystery element is. Let's take a look at this first peak here. We know that the first peak on any spectrograph is going to be the 1s orbital. And right now it's showing a relative intensity, or a relative number of electrons, as 4. But that doesn't make any sense, because the s orbital can only hold a maximum of 2. We'll get back to that in a bit. The next orbital over is all the way over here on this peak. This must be the 2s, because the 2s is next in line. And it too is showing a peak at a relative intensity and number of electrons of 4. Again, that really doesn't make any sense, because the s orbital can only hold 2 electrons. So we have a ratio between these two orbitals of 4:4. Whenever we have a spectrograph that has been printed out to scale, we need to find the lowest common denominator between these two numbers here, between the ratio of 4. And the lowest common denominator is 2 between 4 and 4. So if we take each one of these numbers and divide it by 2. I should have said the least common multiple. The least common multiple between these two would be 2, okay, without it going to 1. And so this means if we divide each of these by 2, we will come up with a 2:2 ratio, which means these peaks are really 2 and 2. Now this makes way more sense, because the s orbital can hold 2 electrons, and before the 1s orbital, or before the 2s orbital starts filling, the 1s orbital will fill completely. So the electron configuration for this is 1s2, 2s2. Now let's ask ourselves, what element on the periodic table has a 1s2, 2s2 electron configuration? Start at hydrogen, 1s1, 1s2, 2s2, 2s2. This mystery element is beryllium. Let's do another example when we have a spectrograph that has not been printed to scale. We'll start with the first orbital right here, and that is the 1s peak. That must mean that this peak next to it is the 2s peak, and this peak is showing a relative intensity of 4, and this peak is showing a relative intensity of 2. Okay, now it makes sense for the 2s to be 2, but it does not make sense for the 1s to be at 4, because again, the s sublevel can only hold a maximum of 2 electrons. So what we have to do is we need to come over here and take a look at our ratio a 4:2 ratio we have here, and find the least common multiple between these two peaks here. And for 4:2, it is going to be 2. That means the ratio is actually 2:1. So this peak really is just 2, and this peak is really just 1. Okay, we do have to change this one as well because it's a ratio between the two peaks here. So this electron configuration is 1s2, 2s1, and let's ask ourselves what element on the periodic table gives us an electron configuration of 1s2, 2s1. Let's come back over here. We'll start at the top. 1s1, 1s2, 2s1. This mystery element is lithium. Okay. And so there's the gist of interpreting a spectrograph in which the peaks are not to scale. The AP exam has been known to do this to students, so make sure that you do know how to interpret one that isn't to scale. Really, it is just a common sense check, because if you were to write this spectrograph without doing the ratio scaling, you would quickly see that if you try to do 1s4, 2s2, something isn't looking right here, because there's no way an s orbital could have more than 2 electrons. And for this one, another common sense check for this would be that, let's say if I were to do the least common multiple between 4 and 4 as being 4, and then I got a ratio of 1:1, that means I would have an electron configuration of 1s1, 2s1, and that is not possible. There is no way the 2s orbital will start filling until the 1s orbital is filled with its 2 electrons. So again, it's just a common sense check in making sure that you're following all the rules of electron configuration. Okay, the next couple of examples will go over how to interpret an overread or non-scaled spectrophotometer.